March 17, 1945. 3 o'clock in the afternoon, the Ludendorff Bridge at Remagen collapsed into the Rhine River with a thunderous roar that echoed through the valley. Twisted steel and concrete crashed into the dark water, taking with it 28 American engineers and the last symbol of German Rhine defenses. But as debris settled in the swift current, something extraordinary was already happening just upstream and downstream from the wreckage. American engineers were completing pontoon bridges across Germany's most sacred defensive barrier faster than German military doctrine considered theoretically possible. At Duisdorf, near Bonn, the so-called Jackpot Bridge stretched 1,145 feet across the Rhine. Construction time, 16 hours and 45 minutes. At Nierstein, 2 pontoon bridges rose from nothing, allowing 60,000 vehicles to cross in a single week. At Oppenheim, engineers completed a heavy pontoon bridge within 24 hours of the initial crossing. These weren't emergency repairs or temporary expedients. These were full-capacity military bridges capable of supporting the heaviest Allied tanks built under enemy fire, constructed faster than German generals believed humanly possible. The speed of American pontoon bridge construction during the Rhine crossings represented a psychological shock that shattered German confidence as completely as any military defeat. It demonstrated that American industrial engineering had evolved beyond European comprehension, that traditional limitations were merely conventions, and that the German army faced an enemy whose capabilities exceeded their most pessimistic projections. This is the story of how American military engineers built bridges that German military theory declared impossible. It's about the collision between centuries-old European engineering doctrine and American industrial innovation. It's about the moment when German generals realized that their most fundamental assumptions about warfare, logistics, and the possible had become obsolete overnight. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Rhine River had served as Germany's primary natural defensive barrier since Roman times. Julius Caesar himself understood the psychological and strategic importance of this waterway when he built his famous bridge across it in 55 BC, demonstrating Roman engineering prowess to Germanic tribes. For 2 millennia, crossing the Rhine in force had been the mark of successful conquerors. Napoleon's armies crossed it. The Romans held it as their eastern frontier. Throughout history, the Rhine represented more than a geographical obstacle. It embodied the boundary between victory and defeat, between invasion and defense. By 1945, German military engineering had developed sophisticated defensive doctrines around Rhine crossings. These principles emerged from centuries of warfare and were codified during the Great War, when German engineers built elaborate defensive positions along the river's eastern bank. The fundamental assumption underlying all German planning was simple. Any enemy attempting to cross the Rhine would require substantial time to construct adequate bridging, time that German forces could use to organize counterattacks, move reserves, and destroy enemy bridgeheads before they became established. German military engineers calculated crossing times based on traditional European construction methods. Their own Brückengerät K equipment, the standard bridge system of armoured engineer units, required careful planning, specialised equipment, and methodical construction procedures. A typical German pontoon bridge, capable of supporting 16-ton loads, demanded days of preparation, skilled engineer personnel, and favourable conditions. German doctrine assumed that any enemy would face similar constraints. The German army's bridging capabilities reflected this methodical approach. Their Brückengerät B system used box girder bridges mounted on 3-compartment pontoons that could be assembled in sections 2, 3, or 4 girders wide. Construction required specialized teams, careful coordination, and substantial time. German engineers were skilled and methodical, but their entire system prioritized durability and engineering precision over speed. The concept of building major bridges in hours rather than days simply didn't exist within German military thought. This methodical approach extended throughout German military culture. German engineering education emphasized theoretical understanding, careful planning, and systematic execution. Military engineers trained in technical schools where precision took precedence over improvisation. The German system produced excellent engineers, but engineers who thought within carefully defined parameters. Speed was secondary to technical perfection. When German commanders planned Rhine defences in early 1945, they based their calculations on these traditional assumptions. Enemy crossing attempts would require substantial preparation time, allowing German forces to detect preparations, mass artillery fire, and organize counterattacks. The geography of the Rhine seemed to support these assumptions. The river averaged over 1,300 feet wide, with swift currents and steep banks in many locations. Traditional military engineering suggested that any serious crossing attempt would require days of visible preparation. German intelligence had observed Allied bridging operations in Italy and France, but these operations seemed to confirm traditional assumptions about construction timelines. Bailey bridges, while faster than conventional construction, still required substantial time for assembly. Pontoon bridges appeared temporary and vulnerable. Nothing in German intelligence suggested that Allied engineers had fundamentally revolutionized bridge construction speed. The psychological dimension was equally important. German military tradition emphasized the natural advantages of defensive positions. The Rhine represented the ultimate defensive position, a major water barrier where defenders held all the advantages. Crossings could be observed, artillery could target construction sites, and any enemy bridgehead would be vulnerable to counterattack. The entire German defensive system assumed that crossing the Rhine would be a prolonged operation, allowing time for effective response. This confidence in Rhine defences extended to the highest levels of German command. Hitler's proclamations about defending the Rhine reflected genuine belief that this barrier could halt Allied advances. German generals shared this confidence, based on centuries of military experience and their understanding of engineering limitations. The Rhine wasn't just a river. It was a guarantee that Germany's heartland remained protected by natural and temporal barriers. The materials and logistics of traditional bridge construction supported these assumptions. Conventional military bridges required substantial quantities of specialized equipment. Pontoons had to be manufactured, transported, and assembled. Bridge decking demanded careful fitting. Support structures required engineering expertise. The entire process was labor-intensive, time-consuming, and vulnerable to disruption. German planners calculated that even successful enemy crossing attempts would provide substantial warning time, but American military engineering had evolved beyond German comprehension. The transformation began years before the Rhine crossings, driven by industrial approaches that prioritized speed, standardization, and mass production over traditional craftsmanship. American engineers hadn't simply improved existing methods, they had fundamentally reimagined how bridges could be built. The American pontoon bridge system represented a complete departure from European practice. Instead of custom-fitted components requiring skilled assembly, American engineers used standardized, interchangeable parts that could be assembled quickly by trained crews. Instead of elaborate preparation, American methods emphasized rapid deployment and immediate construction. Instead of prioritizing permanent solutions, American engineers focused on adequate solutions that could be built immediately. American engineer training reflected this philosophical difference. While German engineers learned systematic methodology, American engineers learned improvisation. While German engineers focused on theoretical perfection, American engineers emphasized practical results. While German engineers worked within established parameters, American engineers were encouraged to find new solutions to old problems. The equipment differences were equally fundamental. American pontoon bridges used mass-produced components designed for rapid assembly. Standardized pontoons could be connected quickly without specialized tools. Pre-fabricated decking sections eliminated time-consuming fitting procedures. The entire system was designed for speed rather than elegance, for adequacy rather than permanence. Most importantly, American engineers had developed systematic procedures that transformed bridge construction from a craft into an industrial process. Specialized crews handled specific tasks in coordinated sequence. Equipment was pre-positioned for immediate use. Construction proceeded continuously rather than in discrete phases. The entire process resembled factory production more than traditional engineering. When American forces reached the Rhine in March 1945, they brought capabilities that German defenders couldn't comprehend. The capture of the Ludendorff Bridge at Remagen on March 7th provided the first demonstration, but the systematic construction of pontoon bridges across multiple crossing sites revealed the full scope of American capabilities. The numbers tell the story. At Remagen, even before the famous bridge collapsed, American engineers had completed backup pontoon bridges. The 51st Engineer Combat Battalion built a heavy pontoon bridge in 27 hours. The 291st Engineer Combat Battalion constructed an M2 steel treadway bridge in under 30 hours while under enemy artillery fire. These weren't emergency expedients. These were full-capacity bridges built faster than German doctrine considered possible. At Oppenheim, where General Patton's Third Army crossed on March 22nd, engineers completed a heavy pontoon bridge within 24 hours of the initial crossing. The speed astounded German defenders who had expected days of warning before serious bridging began. Instead, they faced completed bridges capable of supporting heavy armor before they could organize effective counterattacks. The construction at Nierstein demonstrated the full scope of American capabilities. 2 pontoon bridges rose simultaneously, each capable of handling massive traffic volumes. Within a week, 60,000 vehicles had crossed these bridges, more traffic than German planners had imagined possible across Rhine bridges built in such short timeframes. The speed of construction, matched by immediate high-volume utilization, proved that American bridges weren't temporary expedients but serious engineering achievements. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But perhaps the most psychologically devastating demonstration came at Duisdorf, near Bonn, where American engineers built what became known as the Jackpot Bridge. 1,145 feet long, this pontoon bridge was completed in 16 hours and 45 minutes. The name itself, Jackpot Bridge, reflected American confidence and casual efficiency. What German engineers would have considered a major construction project requiring extensive planning and preparation, American engineers completed in less than a day and named like a gambling prize. The systematic nature of these achievements revealed their true significance. This wasn't luck or exceptional circumstances. This was standard American capability applied systematically across multiple crossing sites. While German defenders struggled to comprehend what was happening at one location, similar achievements were occurring simultaneously across the entire Rhine front. German reactions evolved from disbelief to alarm to despair. Initial reports were dismissed as exaggerated or misunderstood. Traditional military thinking suggested that such rapid construction speeds were impossible. German commanders assumed that American bridges were temporary structures unsuitable for serious military traffic. Reality proved devastatingly different. Generaloberst Alfred Jodl, Hitler's operations chief, initially refused to believe intelligence reports about American bridge construction speeds. When presented with photographic evidence, he questioned whether American structures could support significant military loads. When heavy Allied armor began crossing these bridges in substantial numbers, German command faced a crisis of comprehension. Their fundamental assumptions about warfare logistics had proven catastrophically wrong. Field Marshal Albert Kesselring, commanding German forces in the West after being transferred from Italy, understood the implications immediately. His experience in Italy had exposed him to Allied engineering capabilities, but the Rhine crossings revealed capabilities beyond even his pessimistic assessments. In a dispatch to Berlin on March 18th, he acknowledged that Allied bridge construction proceeded at speeds that made conventional defensive planning obsolete. The psychological impact extended beyond immediate tactical concerns. German military doctrine was based on tempo, the assumption that defensive forces could observe enemy preparations and respond appropriately. American bridge construction speeds eliminated this temporal advantage. By the time German forces identified crossing attempts, American bridges were already operational and supporting major military formations. German artillery, traditionally the primary tool for disrupting river crossings, proved inadequate against American construction speeds. Artillery fire that might have prevented bridge construction over several days couldn't stop construction completed in hours. American engineers often finished bridges faster than German artillery could be repositioned and targeted effectively. The industrial scale of American operations compounded German psychological distress. This wasn't desperate improvisation or heroic individual effort. This was systematic, repeated, industrial-scale engineering that suggested unlimited American capabilities. Each successful bridge demonstrated not just immediate tactical success, but overwhelming industrial superiority. German engineer officers, trained in methodical precision, found American achievements incomprehensible. Captain Wilhelm Friesenhahn, the engineer officer responsible for destroying the Remagen Bridge, survived capture and interrogation. His statements revealed deep confusion about American methods. How could bridges be built so quickly without compromising structural integrity? How could such rapid construction produce bridges capable of supporting heavy military traffic? These questions reflected a fundamental misunderstanding of American engineering philosophy. German engineers assumed that speed and quality were mutually exclusive. American engineers had proven that proper systematization could achieve both simultaneously. Standardization enabled speed without sacrificing capability. Mass production eliminated custom fitting without reducing strength. The broader implications terrified German command. If American engineers could build major bridges in hours rather than days, what other assumptions about American capabilities had proven wrong? If traditional defensive advantages based on natural barriers could be overcome so quickly, what defensive positions remained viable? The Rhine crossings revealed that American industrial capacity had evolved beyond German comprehension. The bridges themselves were only visible manifestations of underlying industrial and organizational capabilities that dwarfed German resources. Each pontoon section represented American aluminum production. Each bridge demonstrated American transportation capabilities. Each completed crossing proved American organizational efficiency. German attempts to counter American bridge construction proved futile. Artillery fire that might have disrupted traditional construction barely slowed American operations. Air attacks against bridge sites found targets that appeared and became operational faster than mission planning could accommodate. Even successful attacks against individual bridges proved meaningless when replacement bridges appeared within hours. The V-2 rocket attacks against the Remagen Bridge illustrated German desperation. Hitler ordered up to 100 rockets fired against the bridge over 2 days, but rocket troops could only manage 11 launches. Even this desperate measure failed to prevent American exploitation of Rhine crossings. By the time rockets fell near Remagen, multiple American bridges were already operational across the entire Rhine front. The speed of American bridge construction eliminated German strategic options. Traditional doctrine assumed that river barriers would provide time for reserve mobilization, defensive preparation, and counterattack organization. American bridges provided no such time. German forces found themselves facing established Allied bridgeheads before defensive measures could be implemented. The psychological transformation was complete. German commanders, who had confidently planned Rhine defenses based on traditional engineering limitations, now faced an enemy whose capabilities exceeded their worst-case scenarios. The realization that fundamental assumptions about warfare had become obsolete created panic that contributed to rapid German collapse. General Heinz Guderian, dismissed by Hitler in March 1945, later wrote that the Rhine crossings demonstrated American capabilities that German planners had never seriously considered. The speed of bridge construction suggested industrial and organizational advantages that made continued resistance pointless. Germany faced an enemy whose basic capabilities exceeded German theoretical maximums. The transformation extended beyond immediate military considerations. German engineer officers, observing American construction methods, saw evidence of systematic innovation that challenged their understanding of engineering itself. American bridges weren't just built quickly. They were built using methods that German engineering education hadn't envisioned. American standardization enabled interchangeability that eliminated traditional assembly problems. American mass production provided unlimited component availability. American organization coordinated multiple specialized teams working simultaneously rather than sequentially. The entire process reflected industrial thinking applied to military engineering. Most significantly, American engineers demonstrated that traditional limitations were often arbitrary constraints rather than natural laws. The assumption that major bridges required extensive construction time proved false when proper methods and adequate resources were applied systematically. The Rhine crossings showed that human capability exceeded conventional expectations when artificial limitations were abandoned. The German Army's excellent engineers proved capable of learning American methods, but learning occurred too late to affect the war's outcome. German prisoners working on post-war bridge reconstruction under Allied supervision quickly adapted to American techniques. Their rapid adaptation proved that capability differences reflected systematic approaches rather than inherent limitations. The long-term implications extended far beyond the immediate military situation. The Rhine crossings demonstrated that American industrial methods could revolutionize any field when properly applied. Traditional assumptions about time requirements, resource needs, and technical limitations could be challenged through systematic innovation and adequate resources. American pontoon bridge construction during the Rhine crossings represented more than tactical engineering success. It demonstrated the transformation of warfare through industrial innovation. It proved that systematic thinking could overcome traditional limitations. It showed that American approaches to problems could achieve results that European methods considered impossible. The bridges themselves became symbols of broader American capabilities. Each successful crossing demonstrated not just immediate military success, but underlying industrial and organizational advantages that determined the war's outcome. The speed of construction proved that American resources were not just larger than German resources, but were organized more effectively. The psychological impact on German leadership proved as devastating as immediate military consequences. Commanders who had based defensive planning on traditional assumptions about engineering limitations discovered that their fundamental understanding of warfare had become obsolete. The realization that American capabilities exceeded their theoretical maximums created despair that accelerated German collapse. The systematic nature of American achievements eliminated hope that Rhine crossings represented exceptional circumstances. Multiple bridges built simultaneously across hundreds of miles of front demonstrated that rapid construction was standard American capability rather than desperate improvisation. German forces faced an enemy whose routine performance exceeded German theoretical limits. Most importantly, the Rhine crossings revealed the broader transformation of warfare through industrial innovation. American engineers hadn't simply improved existing methods. They had created entirely new approaches that rendered traditional limitations meaningless. The bridges represented visible proof that systematic innovation could achieve what previous generations considered impossible. The legacy of American pontoon bridge construction at the Rhine extended far beyond the immediate military situation. The methods developed under combat pressure influenced post-war construction practices worldwide. The speed achievements established new expectations for engineering timelines. The systematic approaches demonstrated possibilities that shaped subsequent infrastructure development. Modern military engineering traces its roots to innovations pioneered during the Rhine crossings. Contemporary rapid deployment bridges use principles established by American engineers in 1945. Current expectations for construction speed stem from demonstrations that such pace was achievable when proper methods and adequate resources were applied systematically. The psychological breakthrough proved equally significant. The Rhine crossings demonstrated that traditional limitations often existed only in minds rather than reality. Determined effort, guided by systematic thinking, could achieve what others considered impossible. The bridges built in hours didn't violate natural laws. They operated under different principles that expanded human capability. For German generals who had never imagined that pontoon bridges could carry armies across the Rhine in hours, the reality proved devastating. Their careful defensive planning based on traditional assumptions crumbled when faced with American capabilities that exceeded their comprehension. The Rhine, Germany's most sacred defensive barrier, fell not to superior numbers or overwhelming firepower, but to engineering innovation that rendered traditional limitations obsolete. The bridges rose overnight, carrying American armies into Germany's heartland, and carrying with them proof that human ingenuity, properly organized and equipped, could accomplish feats that previous generations would have considered miraculous. When contemporary engineers face seemingly impossible deadlines, they can look back to March 1945 for inspiration and practical proof that systematic innovation can overcome any obstacle. The ultimate lesson transcends engineering. When determined people question fundamental assumptions, organize systematically, and apply available technology creatively, they can achieve what others consider impossible. The pontoon bridges that spanned the Rhine in hours didn't represent violations of natural law. They demonstrated what became possible when artificial constraints were abandoned and human capability was properly directed. The German generals, who never imagined such achievements, learned too late that their limitations were conventions rather than natural laws. The American engineers who built those bridges proved that yesterday's impossibility could become tomorrow's routine when systematic innovation was applied to fundamental problems. Their legacy continues inspiring engineers worldwide to push beyond conventional limitations toward new possibilities that await discovery by those willing to question what others accept as impossible. The transformation of military bridge construction during the Rhine crossings revealed broader changes in warfare itself. American success stemmed not from superior individual skill or courage, but from systematic approaches that maximized human capability. Through organization, standardization, and industrial thinking, these methods would reshape military engineering permanently and influence civilian construction practices for decades. The immediate aftermath of the Rhine crossings demonstrated the strategic importance of rapid bridge construction. American forces exploited their bridgeheads so quickly that German defensive planning became meaningless. Traditional military doctrine assumed that river crossings would provide natural pause points, allowing defenders to regroup and counterattack. American bridge construction eliminated these pauses, maintaining offensive momentum that prevented German recovery. The speed of American advances following the Rhine crossings reflected this engineering advantage. Instead of consolidating bridgeheads and preparing methodical attacks, American forces poured across multiple bridges simultaneously, advancing faster than German commanders could coordinate responses. The bridges became highways carrying American armies deep into Germany's industrial heartland before effective resistance could be organized. Statistical analysis reveals the scope of American achievement. Between March 7th and March 31st, 1945, American engineers constructed or completed more than 25 bridges across the Rhine. These weren't temporary expedients, but substantial structures capable of supporting continuous heavy traffic. The combined capacity of these bridges exceeded Germany's ability to destroy them faster than they could be built or repaired. The psychological warfare dimension proved equally significant. German forces observing American bridge construction witnessed capabilities that challenged their understanding of what was possible. The sight of major bridges rising in hours rather than days created despair that contributed to widespread German surrender. Why continue fighting when the enemy possessed capabilities that rendered traditional defensive advantages meaningless? American engineer units had evolved into integrated industrial teams that combined traditional military skills with systematic efficiency. Each pontoon bridge construction involved multiple specialized crews working in coordinated sequence. Site preparation teams cleared obstacles and prepared foundations. Equipment teams positioned pontoons and bridge components. Assembly teams connected sections using standardized procedures. Traffic control teams managed vehicle flow across completed bridges. This systematic approach eliminated the chaos and delays that characterized traditional military engineering. Instead of improvising solutions to unexpected problems, American engineers followed proven procedures that anticipated difficulties and provided standard responses. The entire process resembled factory production more than traditional construction, with predictable timelines and reliable results. The equipment itself reflected this systematic philosophy. American pontoon bridges used components designed for rapid assembly by trained crews rather than skilled craftsmen. Standardized connections eliminated the need for custom fitting. Interchangeable parts allowed flexibility without complexity. The entire system prioritized speed and reliability over elegance or permanence. Training programs had prepared American engineers for rapid deployment scenarios. Unlike German engineers who learned systematic methodology suited for deliberate operations, American engineers trained for speed under pressure. They practiced rapid assembly procedures until they became automatic. They learned to work efficiently in small teams, coordinated toward common objectives. They understood that adequate solutions implemented immediately were superior to perfect solutions that arrived too late. The organizational structure supporting American bridge construction proved equally important. Corps-level engineer commands coordinated multiple battalions working simultaneously across wide fronts. Standardized equipment allowed units to support each other without compatibility problems. Centralized planning provided strategic direction while allowing tactical flexibility. The entire system maximized efficiency while maintaining operational security. American logistics capabilities enabled this systematic approach. Standardized bridge components could be manufactured in large quantities and shipped wherever needed. Transportation assets could move equipment rapidly to construction sites. Supply systems provided continuous material flow without interruption. The bridges reflected not just immediate engineering capability, but underlying industrial capacity that German forces couldn't match. The contrast with German capabilities was stark. German bridge construction relied on skilled engineers using specialized equipment in carefully planned operations. German methods produced excellent results but required substantial time and favorable conditions. German systems couldn't adapt quickly to changing circumstances or compete with American construction speeds under combat conditions. The capture of German engineer officers provided insight into their thinking. Interrogation reports reveal genuine confusion about American methods. German engineers couldn't understand how adequate structural strength could be achieved so quickly. They assumed that rapid construction required engineering shortcuts that would compromise bridge capacity. American bridges, carrying heavy tank traffic without structural problems, challenged fundamental German assumptions about construction requirements. These captured engineers quickly learned American methods when assigned to post-war reconstruction projects. Their rapid adaptation proved that capability differences reflected systematic approaches rather than inherent limitations. German engineers, working under American supervision, achieved construction speeds they had previously considered impossible. The methods themselves were learnable. The systematic thinking behind them represented the crucial innovation. The broader implications extended beyond immediate military applications. American engineering approaches developed during the war influenced post-war infrastructure development worldwide. Rapid construction methods pioneered under combat pressure found civilian applications in highway construction, disaster relief, and industrial development. The systematic thinking that enabled rapid bridge construction shaped approaches to large-scale engineering projects for decades. International engineering exchanges following the war spread American methods globally. European engineers studying in America learned systematic approaches that prioritized speed and efficiency. American engineering firms winning overseas contracts brought these methods to international projects. Technical publications documented procedures that had proven effective under extreme conditions. The psychological breakthrough proved equally significant for civilian applications. The Rhine crossings demonstrated that traditional construction timelines often reflected conventional thinking rather than natural limitations. When systematic approaches and adequate resources were applied intelligently, construction speeds could exceed conventional expectations by dramatic margins. Modern military engineering incorporates lessons learned during the Rhine crossings. Contemporary rapid deployment bridges use principles established by American engineers in 1945. Current doctrine emphasizes speed and standardization over custom solutions. Training programs stress systematic procedures and coordinated teamwork. The fundamental approaches pioneered during the Rhine crossings remain relevant to modern military engineering challenges. Civilian infrastructure development adopted similar principles. Highway construction projects employ systematic approaches that prioritize speed without compromising quality. Standardized components enable rapid assembly and reliable performance. Project management techniques coordinate multiple teams working simultaneously toward common objectives. The transformation initiated during the Rhine crossings shaped modern construction practices across multiple industries. The economic implications were substantial. Rapid construction methods reduced project costs through shorter timelines and more efficient resource utilization. Standardization enabled mass production economies that reduced component costs. Systematic approaches minimized delays and cost overruns that plagued traditional construction projects. The methods proven during the Rhine crossings provided competitive advantages that influenced post-war economic development. Quality control evolved to support rapid construction without compromising performance. Statistical methods identified problems before they affected structural integrity. Standardized testing procedures verified component quality. Systematic inspection protocols ensured that speed didn't compromise safety. The Rhine crossings proved that rapid construction and high quality were compatible when proper methods were employed. Environmental considerations, while less prominent than in contemporary practice, were addressed efficiently through systematic approaches. Standardized mitigation measures prevented lengthy environmental assessments. Rapid construction minimized the duration of environmental disruption. Systematic restoration procedures restored natural conditions after temporary bridges were removed. The training revolution that enabled rapid bridge construction influenced military education permanently. Engineering schools incorporated systematic procedures into standard curricula. Practical exercises emphasized speed and coordination under pressure. Leadership development stressed the importance of systematic thinking and resource optimization. The educational approaches that produced effective bridge construction teams shaped military engineering training for decades. Research and development accelerated innovation in bridge construction technology. Industry collaboration produced improved materials and construction methods. Government investment in engineering research yielded practical advances that found both military and civilian applications. The competitive pressure to achieve rapid construction speeds drove technological advancement that benefited society broadly. The psychological transformation of American engineers proved as important as technological advancement. Engineers who had successfully built major bridges under combat conditions approached subsequent challenges with confidence that traditional limitations could be overcome through systematic effort. This psychological change contributed to post-war infrastructure achievements that seemed impossible by pre-war standards. International influence spread American engineering approaches worldwide through multiple mechanisms. Foreign students trained in American engineering schools returned home as advocates for systematic construction methods. American firms winning international contracts demonstrated effective techniques to local engineers. International organizations adopted American standards that emphasized speed and efficiency. The computer revolution, beginning in the 1950s, amplified advantages established during the Rhine crossings. Design optimization became feasible for complex projects. Scheduling coordination became manageable for multiple simultaneous operations. Resource allocation became systematic rather than intuitive. The mathematical precision that computers enabled complemented the systematic thinking that had proven effective during the Rhine crossings. Materials science advances built upon foundations established during wartime engineering. High-strength materials enabled longer spans and reduced construction time. Improved joining methods simplified assembly procedures. Advanced testing techniques verified performance under extreme conditions. The materials innovations that emerged from wartime necessity continued improving construction capabilities for decades. Equipment evolution accelerated the trends established during the Rhine crossings. Hydraulic systems replaced mechanical systems for greater precision and reliability. Diesel engines provided portable power for remote construction sites. Electronic controls improved coordination between multiple pieces of equipment. The equipment advancement that began during the war continued making rapid construction more achievable. Management science contributed systematic improvements that extended wartime innovations. Operations research optimized resource allocation for complex projects. Systems engineering coordinated interdependent activities toward common objectives. Human factors engineering improved safety and efficiency in high-pressure construction environments. The management techniques that proved effective during the Rhine crossings influenced project management across multiple industries. The cultural impact extended beyond engineering circles. American confidence in technological solutions grew from wartime engineering successes. The belief that systematic effort could overcome traditional limitations became characteristic of post-war American culture. The engineering achievements during the Rhine crossings contributed to broader cultural optimism about technological progress. International recognition of American engineering capabilities influenced post-war diplomatic relationships. Countries seeking infrastructure development turned to American firms for expertise. International development programs adopted American construction standards. Technical assistance programs spread American engineering methods to developing nations. The reputation established during the Rhine crossings opened international opportunities for American engineers. The legacy, institutions created during the war continued advancing rapid construction techniques. The Army Corps of Engineers incorporated wartime lessons into standard procedures. Engineering professional organizations promoted systematic approaches in civilian practice. Academic institutions developed curricula that emphasized rapid construction methods. The institutional changes initiated during the war shaped engineering practice permanently. Modern applications of principles established during the Rhine crossings extend across multiple fields. Disaster relief operations use rapid bridge construction to restore transportation networks. Military operations employ similar techniques to maintain logistics capabilities. Commercial construction projects adapt systematic approaches to reduce timelines and costs. The fundamental principles pioneered during the Rhine crossings remain relevant to contemporary challenges. The transformation initiated by American engineers during the Rhine crossings represents one of history's most complete technological revolutions. Unlike military secrets that remained classified or industrial processes protected by patents, rapid construction methods spread openly through professional networks. This open dissemination accelerated global infrastructure development beyond what any single nation could have achieved independently. The documented evidence confirms that American bridge construction speeds during the Rhine crossings weren't achieved through shortcuts or compromises, but through fundamental reimagining of construction as an industrial process. By questioning every assumption, optimizing every operation, and integrating every innovation, American engineers achieved speeds that redefined what was possible. Modern infrastructure exists because of breakthroughs achieved during this transformative period. Contemporary expectations for construction speed stem from demonstrations that such pace was achievable when proper methods and adequate resources were applied systematically. The bridges that rose across the Rhine in hours established standards that continue challenging engineers worldwide. When German generals declared American pontoon bridge construction speeds impossible, they were correct within their paradigm. American engineers had created new paradigms where previous impossibilities became routine achievements. This transformation represents human progress at its finest, the expansion of capability through systematic innovation and determined effort. The technical specifications of American pontoon bridges revealed the sophistication beneath apparent simplicity. The M1938 pontoon bridge system used aluminum alloy pontoons that weighed substantially less than traditional steel alternatives, while maintaining superior buoyancy characteristics. Each pontoon measured 25 feet in length and could support distributed loads exceeding German calculations for comparable structures. The aluminum construction resisted corrosion from Rhine water while providing strength-to-weight ratios that German engineers had not encountered in their theoretical studies. The standardized connection system eliminated the complex fitting procedures that characterized European bridge construction. American pontoons used mechanical connections that could be assembled by crews wearing heavy gloves in darkness or adverse weather conditions. The entire system was designed for soldiers rather than skilled craftsmen, recognizing that combat conditions demanded simple, reliable procedures that worked under stress. American training manuals documented construction procedures with precision that reflected industrial thinking applied to military engineering. Step-by-step instructions eliminated guesswork and ensured consistent results regardless of crew experience levels. Timing charts provided benchmarks for each construction phase, allowing commanders to predict completion times with accuracy. German planning had never achieved. The entire system reflected American confidence that complex tasks could be systematized and taught to ordinary soldiers. The pneumatic float system represented another American innovation that German engineers failed to anticipate. These rubber pontoons could be inflated rapidly using portable compressors, eliminating the transportation problems associated with rigid pontoons. Deflated floats occupied minimal shipping space, allowing engineers to carry bridging materials for multiple crossings without overwhelming transportation assets. When inflated, these floats provided buoyancy comparable to traditional pontoons while weighing significantly less. Quality control procedures ensured that rapid construction didn't compromise structural integrity. American engineers used load testing protocols that verified bridge capacity before committing heavy equipment to crossing operations. Statistical sampling techniques identified defective components before they could cause failures. The systematic approach to quality control demonstrated that speed and reliability were compatible when proper procedures were followed consistently. The psychological preparation of American engineer crews proved as important as technical training. Unlike German engineers who worked within established hierarchies emphasizing technical expertise, American engineers were trained to think independently and solve problems creatively. They understood that combat conditions would demand improvisation within systematic frameworks. This psychological flexibility enabled rapid adaptation to unexpected circumstances without abandoning proven procedures. Communication systems coordinated multiple construction teams working simultaneously across wide river frontages. Radio networks allowed real-time coordination between bridge sites, equipment suppliers, and traffic control units. Standardized terminology eliminated confusion between units from different commands. The communication infrastructure enabled systematic coordination that multiplied individual team effectiveness. The economics of American bridge construction revealed advantages that extended beyond immediate military applications. Mass production techniques reduced component costs below German estimates for comparable equipment. Standardization enabled interchangeability that eliminated the custom manufacturing required by German systems. The economic advantages reflected industrial capabilities that German planners had underestimated throughout the war. American innovations in materials handling accelerated bridge construction beyond German comprehension. Mechanical equipment moved pontoons and bridge sections with speed and precision that manual methods couldn't match. Specialized vehicles delivered components directly to assembly points, eliminating time-consuming manual transportation. The entire logistics system was designed to support rapid construction rather than deliberate assembly. Weather resistance built into American bridge systems enabled construction under conditions that would have halted German operations. Waterproof electrical connections functioned reliably in Rhine winter conditions. Anti-slip surfaces provided traction for vehicles crossing in rain or snow. The system reliability under adverse conditions reflected American understanding that military equipment must function regardless of weather. Safety procedures protected construction crews without significantly slowing assembly operations. Standardized safety equipment reduced accident rates even under combat conditions. Emergency response procedures minimized the impact of equipment failures or injuries. The systematic approach to safety demonstrated that rapid construction and crew protection were compatible objectives when proper planning was implemented. The scaling capabilities of American bridge systems enabled rapid expansion when tactical situations demanded increased capacity. Additional pontoon sections could be added to existing bridges without rebuilding entire structures. Parallel bridges could be constructed using identical procedures and equipment. The modular design philosophy enabled tactical flexibility that German rigid systems couldn't match. American maintenance procedures kept bridges operational despite combat damage and heavy traffic. Rapid repair techniques restored damaged sections without interrupting traffic flow. Preventive maintenance procedures identified problems before they caused failures. The systematic approach to maintenance reflected understanding that bridge construction was only the beginning of sustained operations. The integration of American bridge construction with broader logistical systems multiplied its strategic impact. Transportation planning coordinated bridge capacity with traffic requirements. Supply systems provided continuous material flow to support extended operations. The systematic integration demonstrated that bridge construction was only one element of comprehensive logistical capabilities that German forces couldn't match. Engineering documentation recorded construction procedures with precision that enabled continuous improvement. After-action reports identified problems and solutions for future operations. Technical manuals incorporated lessons learned from combat experience. The systematic approach to documentation created institutional knowledge that improved performance throughout the war. Training evolution reflected American ability to adapt procedures based on combat experience. Initial training programs emphasized basic techniques suitable for European conditions. Combat experience revealed requirements for faster assembly under fire. Training programs evolved to address these requirements, producing engineer crews capable of achieving construction speeds that exceeded even American initial projections. The Rhine crossings proved that traditional limitations often exist in Christ minds rather than reality. When artificial constraints are removed and human capability is properly organized, achievements that seem impossible become achievable through systematic effort. The pontoon bridges that carried American armies across Germany's most sacred defensive barrier demonstrated that human ingenuity, properly directed, knows no limits. Technical innovation continued accelerating after the Rhine crossings as American engineers incorporated combat lessons into improved procedures. Post-war bridge construction adopted techniques proven under extreme conditions. Civilian applications adapted military innovations to peacetime requirements. The technological advancement that began during the Rhine crossings continued influencing construction practices for decades. International cooperation spread American engineering techniques worldwide through professional exchanges and technical assistance programs. European engineers studying American methods learned systematic approaches that challenged traditional limitations. Developing nations adopted American standards that emphasized rapid construction and systematic procedures. The global dissemination of American techniques transformed international engineering practice. The educational transformation initiated during the Rhine crossings influenced engineering curricula permanently. Universities incorporated rapid construction techniques into standard programs. Professional development programs emphasized systematic thinking and project coordination. The educational changes that produced effective bridge construction teams shaped engineering education for generations. Research and development investments yielded continuous improvements in bridge construction technology. Industry collaboration produced advanced materials and improved construction methods. Government funding supported innovation programs that benefited both military and civilian applications. The research momentum that began during the Rhine crossings continued, driving technological advancement throughout the post-war period. The cultural impact extended throughout American society as engineering successes influenced broader attitudes toward technological challenges. The confidence that systematic effort could overcome traditional limitations became characteristic of American approaches to complex problems. The engineering achievements during the Rhine crossings contributed to cultural optimism about technological progress that shaped post-war American society. Economic growth both enabled and resulted from construction capabilities demonstrated during the Rhine crossings. Industrial capacity that produced bridge components supported post-war infrastructure development. Engineering expertise proven under combat conditions found civilian applications in highway construction and urban development. The economic advantages gained during the war continued benefiting American society for decades. The German generals who never imagined such rapid bridge construction learned too late that their assumptions were conventions rather than natural laws. The American engineers who built those bridges in hours rather than days left a legacy that continues inspiring engineers worldwide to question conventional limitations and pursue new possibilities that await those willing to think systematically about fundamental problems. Today, when engineers face seemingly impossible deadlines or insurmountable obstacles, they can draw inspiration from March 1945, when American engineers proved that systematic innovation could overcome any barrier. The bridges that spanned the Rhine in hours didn't violate natural laws. They demonstrated what becomes possible when human determination, industrial capability, and systematic thinking combine toward common objectives. The ultimate lesson transcends engineering and warfare. It demonstrates that human achievement knows no limits when artificial constraints are abandoned and genuine capability is properly organized toward worthy objectives. The American engineers who bridged the Rhine in hours proved that yesterday's impossibility can become tomorrow's routine when systematic innovation replaces conventional thinking. Their legacy endures in every rapid construction project, every systematic approach to complex problems, and every refusal to accept traditional limitations as natural laws. The bridges themselves may have been temporary, but the transformation they represented proved permanent. They carried more than American armies across the Rhine. They carried proof that human capability, properly organized and directed, can achieve what others consider impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.